Alright, so we're just going to continue going through quadratics now. So you did a lot of this last year in grade 10, finding the maximum and minimum values of a quadratic from various different forms. So we're going to spend some time reviewing how you would have done that back in grade 10. And once you've done that, we're going to step it up a little bit and do some more 3U type problems. So first thing you're going to want to remember, just as a bit of a recap here, again, if you were trying to find information from a quadratic, how you do it depends on what form you're in. So here we're specifically looking for the optimal value of the graph. So the optimal value, remember, comes from the vertex, and it's going to be specifically the y value of the vertex. So if you're in vertex form, that's when it's the absolute easiest because you're already have the vertex staring at you. The optimal value is that k, so it's kind of staring at you right there. Factored form, if you want to find the vertex, you're going to find the zeros first. Once you find the zeros, you find the axis of symmetry. So that axis of symmetry in the equation to find that optimal value. And from standard form, you have lots of options. You're trying to get from standard form into vertex form, so you could either complete the square or use partial factoring. If you complete the square, you go directly into vertex form. If you factor or use partial factoring, you got to find the axis of symmetry from there, and then again, so that axis of symmetry into the equation. So we're going to go through examples of all these different these forms just to remind ourselves of how things worked in grade 10. Okay, so let's look at our first one here. So you got f of x equals 3, x minus 5 all squared minus 17. So first thing you're going to notice, we are in vertex form. And if we're in vertex form, we can get a lot of information about the optimal value. So first of all, if we want to figure out if it's a maximum or a minimum, well, that's going to depend on the direction of opening. So remember that if we open down, we have a maximum. And if we open up, we're going to have a minimum. So if you look at the equation right here, our a value is positive, which means that we open up. So if we're opening up, then our optimal value is going to be a minimum. So once that's out of the way, we can actually define the optimal value. So looking at this function right here, we're in vertex form. Our vertex here is going to be at 5, negative 17. Okay, so our optimal value is going to be our minimum value, which in this case is just going to be negative 17, that y value of the vertex. Okay, last but not least, we're trying to find the domain and range of the inverse in this case. Now, whenever, this sort of came up in the first unit, whenever you're trying to find the domain and range of a parabola, you need to have the vertex. So you need to be in vertex form. As long as you have the vertex and a direction of opening, you can find the domain and range of the function. And we'll worry about the inverse afterwards, but at least now, based on our equation, let's try and find the domain and range of that function. Okay, so I'm just going to bring the function down here so we have it for reference. So if I just want to do a quick little sketch of this guy, nothing too fancy, just make my Cartesian plane here. So my vertex is at 5, negative 17. So that's going to be somewhere down in this quadrant. That's my vertex. And I open up. Okay, so right from here, I can say the domain of this function, it's a parabola, and there's no real-life restrictions on it, so our domain is going to be x equal to the real numbers. And our range depends on our vertex. We're going to have any y value above or equal to negative 17 as possible. So our range will be y is greater than or equal to negative 17. Now, this is all the domain range for the function. This has nothing to do with the inverse. But the one thing you might remember about the inverse, that the domain range of the inverse and the function are related to each other. So if we're trying to find the domain range of the inverse, and we have the domain range of the original function, we just need to switch them. So the domain of our function becomes the range of our inverse, and the range of our function becomes the domain of the inverse. So you notice here we didn't actually have to actually find the equation of the inverse. All we need to do is work with the original equation and then swap those domain ranges to find the domain range for our inverse. Okay, so let's move on. This was an example of one in vertex form. Now let's take a look at one in factored form. So I want you guys to try this on your own. See if you can answer all these questions right here. So whether the optimal value is a max or min, what the optimal value is, and the domain and range. So pause it and push play when you're ready to see the answers. Okay, so you can see the answers there. Let's just go through them quickly. First one you might have fallen into a little bit of a trap there. It's very tempting to look at the a value in front here and just say, oh look, this a value here is negative, therefore my parabola opens down, so my optimal value is a maximum. But you have to be very, very careful, because if you look at inside the brackets here, one of the coefficients of x happens to be negative here. So if you were to expand this into standard form, you would actually wind up with something along the lines of, well, if you look at the coefficients, you've got -1 here, 2 here, and -2. Multiplying those together, our coefficient of x squared in standard form is going to be -2 times 2, -4 times -1. So you're actually going to have 4x squared plus whatever else. Okay, I don't know what the rest of the equation is. I don't need to find it. If all I care about is my direction of opening, this is all I need to look at, my a value from standard form. So looking at standard form, the a value is positive, so we open up, and since we open up, our optimal value is going to be a minimum. Okay, so once we got past that little trap, let's try and find the optimal value. Now, we're in factored form, so once we're in factored form, we can find the x-intercepts. So my x-intercepts for here, I get the first one from my first factor of 2x plus 1, set that equal to 0, and I get x equals -1/2. From the second factor, I get 3 minus x equals 0. Solving that, I get x equals 3. So those give me my x-intercepts, and now I can find my axis of symmetry. Add my two x-intercepts together, divide by 2. And that should give me 5/4. Okay, remember that that's the x value of vertex. You need to find the y value of your vertex. So we sub this 5/4, the axis of symmetry, into the equation here for x. And that will give us our optimal value. Okay, so just skipped ahead, showed the substitution there. When you work this out, you're going to get -2 times 7/2 times 7/4. Okay, when you multiply those together, you get an optimal value of -49/4. Okay. With all that in mind now, we can find the domain and range. So we need to be in vertex, at least have the vertex and direction of opening. If you're in vertex form, that might also help, but it's not actually needed. So we know that we open up, and we know our vertex is at -1/2, -49/4. So if we open up, our y value will be greater than or equal to the minimum value there. So our range will be y is greater than or equal to -49/4, or in decimal form, -12.25. And since it's a parabola, the domain is just x now into the real numbers. Okay, I'll let you guys try the next one here. Now we're in standard form. Same types of questions, right? Find whether the optimal value is a max or min, find the optimal value, and find the domain and range. So pause it and push play when you're ready to see the answers. Okay, we're in standard form. So the a value is negative, so we open down. If we open down, the optimal value is a maximum. Now, to find the optimal value, again, you're going to look for the vertex. We're in standard form, so we have some options. We can complete the square. We could try and factor this one. I don't believe this one factors. In fact, if we check the discriminant, b squared minus 4ac. Or times -4 times 9. That will give you 288. So it's not a perfect square. This one actually doesn't factor. So factoring won't work. We could use partial factoring, however. But the other thing that you saw earlier on in the course, and you saw last year, and it's a formula that we proved using partial factoring, is that if you want to find the axis of symmetry from standard form, you can just set x equal to -b/2a. And that's going to be your axis of symmetry. So in this case, if we do that, we'll have -12 over 2 times -4. So simplify that, we get 3/2. So in a quick little step that we found our axis of symmetry, we can sub that into the original equation to get our optimal value. Okay, I won't go through the algebra for this one, just be a matter of squaring the fraction, doing some multiplication, some simplifying, but the answer you should get after all is said and done is 18 for your optimal value. If that's not working out, just come let me know and we'll work through the algebra together. Okay, so with that in mind, quickly to find the domain and range, it's a parabola, so the domain is x and l into the real numbers. There it is right there. And we are opening down with an optimal value of 18. So with a quick little sketch, we could see that our range will be anything, any y value less than or equal to 18. Okay, so that concludes the review of stuff that we did last year in grade 10. Let's try and step up a little bit, do a bit more 3U type stuff. So here's an example here. We're trying to find the mapping rule that's going to go from y equals x squared, our parent function parabola, to this guy over here. And one thing you'll notice here that this equation is in standard form. When we're trying to describe transformations and get mapping rules, we had to have vertex form. So whenever you see a mapping rule for a quadratic, just like trying to find the domain and range of a quadratic, you need to have the vertex or vertex form. So first things first, we need to find vertex form. So you can use any one of the many methods you've seen to get into vertex form, completing the square, partial factoring. You can see if this one factors to find the x-intercepts. I'm going to take the shortcut again. We developed that formula where x equals negative b over 2a. Okay. If you don't like this, feel free to use one of the other methods I just talked about. So take some time, put this into vertex form, and then try and create the mapping rule once you have that. And just push play when you're ready to see the answer. Okay, so hopefully you gave that a try. You can see the outline of the steps there. So first I found the vertex got it to be, first I found the axis of symmetry over here. In step 1 I found it to be 4 over 3. Then I subbed that value in for x into the equation to try and find the optimal value. So I worked through all the fractions and it simplified down to 2/3. So that gave me my vertex at 4 over 3, 2 over 3. With that in mind, I then created the equation in vertex form. So I had my h and my k for my vertex. The a value is the same as the one from standard form. So that gave me my vertex form. Now that I'm in vertex form, I can create my mapping rule. So I wind up with x plus 4 over 3, and then 3y plus 2 over 3 for my mapping rule. Okay, last example. So I'm giving you a function, negative 2x squared minus 7x plus 3, and I want to find the domain and range of this transformed version of 2f of 3x minus 4 minus 7. A lot of different ways you can go about doing this. You could start by finding f of 3x minus 4, then multiplying it by 2, then subtracting 7, creating that whole new equation, and then trying to find the domain and range of that. And again, it's a quadratic, so we have to put it into vertex form. We could put this into vertex form first, and then find 2f of 3x minus 4 minus 7. Or could even put this one into vertex form and create a mapping rule to go from the original function to this one, and then transform the original domain and range to this one. All of them sound pretty messy. It's really just your choice as to what you want to do. I like just sort of creating this right off the bat to sort of get past that little hurdle the question's giving you to start, and then doing what we did before, putting it into vertex form to find the domain and range. So let's start with that. So I'm going to create 2f of 3x minus 4 minus 7. So f of 3x minus 4, you know your function notation from the first unit. F of 3x minus 4 is going to be all of this function, but every x is replaced with 3x minus 4. So it will be negative 2, 3x minus 4 squared, minus 7 times 3x minus 4 plus 3. Okay, again, this is all from the original function f of x. And I have the minus 7 that's here. So just to remind us of where all these different parts of the equation come from, this 2 is actually from up here. So that's 2 f of 3x minus 4 is this all in here. And then the minus 7 comes afterwards. So this is something that we have to simplify. Let you guys try that on your own. We're just going to quickly finish up this video in part 2. So I'll see you over there.